Hey guys, so this is an introduction to circular motion, and for today I would just like to introduce you a few topics, a few concepts regarding circular motion. So first thing you need to know are a bunch of keywords, these ones essentially. So the first, uniform circular motion. What is this? So anything, whenever something is traveling in a circle at a uniform speed, it's not changing, they are said to be in a uniform circular motion. That's it. That's uniform circular motion, moving in a circle at constant speed. Then you have an angular displacement. What's angular displacement? Well, angular displacement is whenever in a circle some object moves from this point over to this point, right? So it covers a certain amount of angle. This angle is called the angular displacement. How much angle did it displace? And this is measured in radians. If you don't know already, radians is angles measured using pi as a reference point for 180 degrees. So if it's this is roughly 60 degrees, so that's going to be pi by 3 radians. So that's essentially it. That's radians. Then you have angular velocity. Well, angular velocity, if you consider just normal velocity for a second, normal velocity is the change in distance over the change in time, right? In this case, the only thing that changes is that instead of distance, you have change in theta over change in time. And theta is our trusty little angle here, the angle that is angular displacement, essentially, not just any other displacement. That's angular displacement. And that's this thing becomes angular velocity. Right, moving on. So we have, right, now angular velocity is represented using this symbol. It's kind of like a W, but you have to really make it like this for some reason, I don't know. And as we discussed before, this is just angular displacement over time. Now, what do you think that would be for one complete oscillation, right? So when I say one complete oscillation, I mean an object has started from this point, from the center, and went all the way around the circle and came back, right? A full circle. That's one oscillation. So if we change our formula from theta over time period, we know that theta for a full complete revolution would be 2 pi, right? And as you know, we represent the time taken for one complete oscillation by capital T. That's where you get this equation, essentially, the time period. That angular velocity is equal to 2 pi over time period. Then if you just remember that frequency is 1 over time period, you can get to the second part of the equation. Simple derivations, nothing complicated. Right. Then you come across this little concept saying, well, what's the speed essentially of this thing moving around? Because right now all we know is the angular velocity and the angular displacement, how many radians it moves per second. But what about the actual distance? Right, so that's given by a simple derivation. You know that speed equals the distance over time, right? Now for angles, and that can be converted to 2 pi r, which is a circumference. This 2 pi r is a circumference. Sorry. So 2 pi r is a circumference, this entire thing, right? That's our distance because that's what's being covered, divided by the time period. So you essentially get to this part, and then again with the simple derivation you get to that part. But if you remember 2 pi f r, if you remember 2 pi f equal to angular velocity, didn't it? Because 2 pi over t equals angular velocity, and then with a simple derivation you could get to the part where you could say 2 pi 1 over t, and this becomes 2 pi f, right? So angular velocity equals 2 pi f. So what we can do is extract this part and say it as angular velocity, and the radius comes as it is. Therefore we can say that the velocity of our object, not angular, the actual velocity when the object is going around and around in circles, that velocity, that can be said as angular velocity times the radius. And in case you're wondering why even bother, well, here's a really nice thing. So imagine you have two objects, right? One is on the outer circle and one is in the inner circle, right? Now these objects, imagine that they started from here, and they're all connected in the circle, right? And you moved them around from here to here, right? They all went from here to here at this in the same amount of time taken t. Same time, right? They moved at the same time, and we can say that the angle that was covered is the same, the time taken is the same, so their angular velocity is the same, right? Their angular velocity is just v, same. However, you can clearly see that this circumference is bigger than this circumference, right? So if we sorry, this is not angular velocity, right? So their angular velocity is w, pretty simple. But since the radius of oh, I forgot to label them, this is a and this is b, right? Makes it easier. So the radius for a is greater than the radius for b, right? Therefore we can say, if we take this equation, the velocity of a equals theta radius of a, and the velocity of b equals omega, I don't know what's called, I'll just call it angular velocity, rb. And if we take the ratio of these two things, we can say that this thing cancels out, and we have va over vb equals ra over rb, directly proportional, right? So if RA is bigger than RB, definitely VA would be bigger than VB. That's what it depends on. So since the radius is bigger, you can even intuitively sense that A was moving faster because it had to cover a longer distance in the same amount of time. That's where we come to the conclusion that the velocity of A is greater than velocity of B, because the angular displacement is greater. Angular displacement is same, but the radius is greater for A, as A covered more distance. Right, so these are the basic concepts for circular motion. Hopefully there will be more videos similar to this, and have a nice day. Oh, and we'll talk about these in a future class. They're pretty simple, just a recap essentially. But never mind those. Have a good day, guys. Enjoy.